to it once it's conserved. Let me give you a personal from conservation. Conservation sometimes can be powerful. Conservation energy, how fast I don't know anything about the roller coaster. So conservation and conservation, same story. I know what velocity is going to be out, even though I don't know anything about the details of the force of between the two billiard balls or whatever it is. So conservation laws are very powerful. In fact, lots of physicists nowadays say that's the way it goes. So that only two laws, never mind Newton's law or something like that, would be a lot better way of doing things. The opposite opinion. Conservation laws are fantastic, but what they tell you and happen the way it did. That Newton's second law is going to tell you. MA, what the acceleration is, work out all the details. Conservation, look at the situation before, look at the situation afterwards, and ask questions about what happened in the meantime, and you'll be able to extract fantastic information about the outcome. That's all well and good. Tell you the story. How if you want your physics about mechanism, then conservation laws are not going to help you. If you just want to get the answer in a hurry, fantastic. I warn you, we'll do this often. Physics laws are the way to go. So I love conservation. But conservation laws don't tell you about mechanism. And that's, for my money, actually the whole ballgame in physics. Conservation law says that P final is the same as P initial, provided that there are no relevant external forces acting. And then we'll make the statement of relevant external forces acting. There's no mystery about it, but I don't have machinery quite yet. So conservation will says P final is P initial. The classic example of that is collision processes. Now, example, I don't know what number I'm up to. Again. I call the brick wall paradox. It's going to strike you probably as a stupid little paradox, but it is an important thing to resolve this. So that I've got a lump of clay. Its mass is 2 kilograms, and it's going at 3 meters per second, and it's a brick wall. So there's a scene beforehand. That lump of clay sticks onto the brick wall, and here's the scene afterwards. What was the initial momentum when this lump of clay was flying along? It had a mass of 2 kilograms and its speed was 3 meters per second. So P initial is equal to 2 times 3 equals 6. 6 kilogram meters per second. That's the momentum of that lump of clay prior to the collision. What is the momentum after the collision? Zero. Not moving at all anymore. What's going on? I thought this guy said that momentum was always conserved in collisions. Well, that's the paradox. What's going on here? I think there are two different ways that one might think about this problem. So I'll give you the two resolutions. You understand the paradox, first of all. Lump of clay is going along, got some momentum, hits wall, momentum disappeared. Where did it go? What's going on here? Does this mean that law of conservation of momentum is no good? Well, yes and no. First resolution. Well, there was a huge external force acting, so that's precisely my proviso here. What force was acting on this system? I seem to have two elements here, the lump of clay and the brick wall. What external force was acting on that system? Answer, the ground exerted a force on the brick wall, right? In fact, in what direction was it? When the clay hit here, the ground exerted a big force in the backward direction. So the ground actually exerted a force like this. That was a short but large force, and so all bets are off. This is the footnote to the law of conservation of momentum. The law simply was untrue for that case, but we understand why. I don't know if you remember how I got the law of conservation of momentum, but it was from using Newton's third law and the fact that two things were exerting equal and opposite forces on one another, and that's what conservation of momentum emerged from. But that was assuming that the two things are only interacting with one another. If there's a third force acting in the situation, then all bets are off. The proof was no good, and that's exactly what we're seeing here. That's one way of resolving this. A second way is to look at the big picture and realize that that wall was nailed down. It was nailed down to the earth. So let me draw the situation. Here was the lump of clay coming along, and it hit a brick wall that was attached to earth. Not quite to scale here. Then the final scene was brick wall with lump of clay attached to it, attached to the earth, and the whole damn earth recoiled with a velocity w. Now there is no external force acting on the problem, and momentum should be conserved. Well, I believe it was. So what was the initial momentum? The initial momentum was 6 equals the final momentum of earth plus wall plus lump of clay, mass of the earth. You want to worry about the small contribution from the lump of clay there, times the recoil velocity of the earth. Of course, W is a rather small number. It's a small velocity. Why? Because the mass of the earth is rather large. In fact, it's 6 times 10 to the 24th kilograms. I just looked it up. That times W. So that tells me that the recoil of the earth, the 6's conveniently cancel. That's why I chose 6 to be the initial momentum. And I'm left with 10 to the minus 24th. So W equals 10 to the minus 24th meters per second. Now 10 to the minus 24th meters per second is kind of a small velocity. To get a feel for just how small that recoil velocity of the Earth is, let's think. What would be a good scale? How big is an atom? Do you happen to know what the radius of an atom is? Hydrogen atom you might know, especially if you study some chemistry. Anybody know it? I know it in angstroms. It's half an angstrom is the radius of the hydrogen atom. So the diameter of a hydrogen atom would be 1 angstrom. and 1 angstrom is 10 to the 10th meters. So diameter of an atom is about 10 to the minus 10th meter. So how long would it take the Earth, going at 10 to the minus 24th meters per second, to cross an atom, to move that far? There's a point to this story, it's coming in a moment. How long would it take Earth that far? So, here's the question. I throw a lump of clay at a brick wall that's attached to the Earth recoils, and I want to know how long does it take the Earth to move 1 atomic diameter? Well, it's got to go 10 to the minus 10th meters, so 10 to the minus 10th meters is equal to 10 to the minus 24th meters per second times the number of seconds, t. So that tells me that t would be 10 to the 14th seconds, isn't that right? Multiply through, it becomes 10 to the plus 24th, 10 to the 14th seconds. I don't have a good sense of what 10 to the 14th seconds is. Do you happen to remember how many seconds in a year? I worked this out, I think it was like one of the early lectures, a nifty thing that you can easily remember. It's pi times 10 to the 7th seconds is 1 year. 3.14 times 10 to the 7th seconds in 1 year. So the time in years would be 10 to the 14th over pi times 10 to the 7th. Or 10 to the 7th goes into 10 to the 14th, 10 to the 7th is 1 over pi, which is about 1/3, which is about 0.3, times 10 to the 7th years, or 3 million years. That's how long the recoiling Earth would take to move 1 atomic diameter. What I'm trying to tell you is that this is not kind of small, this is very damn small. Which is why we don't notice the Earth jerking around every time somebody throws a baseball or something like that. I mean, in principle, the Earth is recoiling every time a baseball is hit or thrown or something like that. But it's recoiling an amount of velocity that's absolutely minuscule. Why is that true? Simply because the Earth weighs a whole lot compared to any of the stuff that you're likely to be throwing around. So we don't feel the Earth recoiling, jerking around all the time because it's really doing it, I guess, in principle, but the velocity is so minuscule that you're never going to notice it. So there are my 2 resolutions to the brick wall paradox. First one is to say, well, there's an external force. If we're just going to focus on the lump of clay and the brick wall, then we have to say, well, I'm sorry, there's an external force acting on this system, so momentum is not conserved. That's a perfectly correct way of looking at it. But if I want to look at the bigger picture, in which that brick wall is attached to the Earth, there are now no external forces. Momentum is conserved. The Earth does recoil. The Earth soaks up the momentum that was lost by the lump of clay. But the recoil velocity of the Earth is so tiny that you're never going to notice it. This raises a kind of intriguing question, however. Suppose that brick wall is actually moving. Well, you say brick walls don't move. Very well. Let's twist it a little bit and say that the lump of clay, or I'm going to turn it into a ping pong ball now because I want it actually to bounce off elastically. Suppose that ping pong ball hits an oncoming freight train. So here's example 2. It's inspired by this first one, by me thinking, okay, what if the brick wall was moving, and then trying to make it more realistic. So example 2. Ping pong ball going at speed v. Its freight train coming at it with a speed w, let's say. So here's the freight train, and it's coming along at a speed w. And here's the ping pong ball, and it's going at a speed v. So there's a scene of 4. Let's see, ping pong ball going v hits freight train going the other way at speed w, and let's say for the sake of argument the collision is elastic. And I would like to know, of course, what is the final velocity of the ping pong ball. So a little while later, the freight train, after the collision, the freight train is still plowing along at essentially that same speed w, just as in the Earth case. It's going to pick up a little bit of increment because of the impact from the ping pong ball, but that's going to be so totally minuscule that I don't need to worry about it. Why not? Because the freight train presumably is enormously heavier than the ping pong ball. Not as much heavier as the Earth was, but the point of that argument was to show you that if you've got a very heavy object and a very light object, you don't need to worry about the change in velocity of the heavy object. So here's the ping pong ball afterwards. It's bounced off the front of that freight train. It's going this direction with some new speed, v final, and that's what I want to find. What could you tell me about v final? I don't think you can tell me very much offhand, except that it got to be bigger than w, right? I mean, it would be absurd if the velocity of the ping pong ball was less than the velocity of the freight train. That would mean that the ping pong ball is somehow passing right through the freight train. So Vf is surely going to be a number bigger than w, but beyond that, I'm not sure what I can say about it. So here's the scene after. Got a picture? This is a classic type of problem, and let me just tell you, the nice way to analyze it is to think of the system, think of the whole process in the rest frame of the freight train. In other words, let's run along at the same speed as the freight train, so that from our perspective, the freight train is just sitting there at rest. Why is that so nice? What's the whole process look like from that point of view? Here's the freight train, and it's not moving in this reference frame, right? The ping pong ball came along with some speed, bounced elastically off that freight train. So I ask you, what is its speed going the other way right after the collision? Same thing, same as whatever it was coming in, right? So in that reference frame, the elastic collision is trivial. Ping pong ball came in, bounced back. It's kind of like this one here, only in this case I assume that the lump of clay stuck onto the wall. If I'd said instead the lump of clay bounced elastically off the wall, how would that have changed this calculation, as a matter of fact? I guess that I would have said the change in momentum of the lump of clay in that case would have been, it first had 6 G's coming in. After the collision, if it was elastic, it had 6 G's coming out. Total change in momentum would have been 12 G's then. So the only difference would have been that I have a 12 over here instead of a 6 if it had been an elastic collision. But never mind that. Coming back to this problem here, the elastic collision, ping pong ball just hits the stationary now freight car and bounces off elastically with the same speed that it came in. Make sense? But what is the velocity of the ping pong ball coming in if its velocity was v in the ground frame and the train is coming at it with velocity w? Is that exactly the question you were going to ask her? Okay, well, let's think about it. If the ping pong ball is going that way and the freight train is coming this way with speed w, what is the velocity of the ping pong ball relative to the freight train? V plus w, is that pretty clear? Yep. V plus w, so this was coming in at speed v plus w, the velocity of the ping pong ball relative to the freight train, so it comes out with velocity v plus w. Is that Vf? No, Vf was the velocity that it has finally in the ground reference frame, not in the reference frame of the freight train. So now I've got to do the last step in the problem is figure out what its velocity is in the ground frame. If its velocity in the freight train frame, remember this is the frame in which I'm running along to the right with velocity v. So I'm running along, w. I'm running along to the right with speed w, and I see this ball going past me with a speed v plus w. So how fast is it going relative to the ground? V plus 2w. You're too quick. Did everybody catch that? That's the answer. How did I do it? I go to the rest frame of the freight car where I know that it's simply, because it's an elastic collision, this thing came in, came out with exactly the same speed. Then, question. What was its velocity coming in? Well, v plus w relative to the freight car. So its velocity going out is v plus w relative to the freight car. Now, the somewhat subtle question, how fast is it going relative to the ground? I'm running along here with speed w, and I see the ping pong ball come past me at velocity v plus w. How fast is it going relative to the ground? Well, v plus w, the speed is going relative to me, plus the speed that I'm going relative to the ground, which was already w. So v plus 2w. How about that? By the way, I never needed to know the masses of the two. All I needed to know was that the freight car was a whole lot heavier than the ping pong ball. The ping pong ball, as it bounces off the freight car, picks up twice the velocity of the freight car. How about that? Very interesting answer. Of course, one could have solved it by applying law of conservation of momentum and conservation of kinetic energy because it's elastic in this original reference frame, but it would take 45 minutes to do it that way. Whereas if you're thinking about it in the reference frame of the freight car, it actually is something you can do in your head. This may strike you as a very specialized kind of problem, but think about it. Things like this are all over the place. Imagine a pitched baseball, for example, that's been hit by the bat. What's the situation? Baseball comes in at 90 miles an hour, bat hits it at some speed, the speed that the guy's swinging the bat at. Baseball takes off with velocity, the velocity of the pitch plus twice the velocity of the bat. Simple as that. The book, by the way, says that some comment about a bunt. I'm saying that in the case of a bunt, what the guy does is hold the bat absolutely still. The pitch just hits the bat and then it drops straight. That's not true. If you held the bat absolutely still, what would happen? That would be w equals 0. The thing would bounce off, of course, with the same velocity that it came in. So they're telling you that if I understood what they were saying, that the bunt should come off the bat at the same speed that it was pitched in. In other words, it should go right back to the pitcher at 90 miles an hour. That's not a very good bunt, in my opinion. So what is a bunt, actually? Evidently, the bat should be moving backward a little bit, so I guess the guy holds it kind of loose, and the bat is actually, or maybe he pulls back on it. You pull back on it with half the velocity of the incoming pitch. So you pull back on the bat at 45 miles an hour, you would actually drop that ball right down in front of the plate. So I believe that in the bunt, the bat is actually pulled backward somewhere. Of course, that's not an elastic collision. So maybe that's where they take care of business, that a ball hitting the bat is probably far from elastic. So maybe you don't have to pull it back at 45 miles an hour. But that's roughly what's going on there. Let me show you a beautiful demonstration that illustrates this. Suppose that I do, tennis ball. And suppose that I had a much bigger ball, basketball. I do. And now what I propose to do is hold the tennis ball right on top of the basketball and drop them both on the ground. What's going to happen? So when it hits the ground, they're both going at speed v if I drop them simultaneously. The basketball hits the ground, bounces elastically off, and is now heading upward at speed v. It's heading upward at speed v after it's hit the ground, but the tennis ball is still a little bit above it, so the tennis ball is going down with speed v. The basketball is now going upward with speed v. After the collision with the tennis ball, how fast is that tennis ball going to be going? 3v, isn't that right? Because it had v coming down, and then it picks up twice the velocity of the basketball, so it takes off with a speed of 3v. Let's see if we can do this. This doesn't work terribly well in my experience because it's very hard for me to drop these two simultaneously and straight down. So it may bounce off to a side. Hopefully it won't go in your direction, but that sort of did it. What you're supposed to see is that the tennis ball takes off with surprisingly large velocity. Now, of course, these aren't elastic collisions, so we lost something there. This is not infinitely heavy or even 10 to the 24th times as heavy as this, so it doesn't quite fit this theory, but it's close enough. Hey, fairly impressive, huh? You know, if you want to see this thing done beautifully, there exists a toy which I tried to buy around here, but I can't find it anywhere. I wonder if maybe it's now illegal. Because it actually, although it has nothing but 5 Super Balls on it and a little stick, it can achieve fantastic velocities. And probably even in this room, it would not be entirely safe to fuss with this. But the Astro Blaster, that's what it's called. Has anybody seen one?
My physics teacher brought it in last year to class and did the same demo.
He did it?
Yeah.
In a small room?
Yeah, it was
Because
like,
it would poke holes in the
yeah,
ceiling.
it went all the way up. He only like dropped it an inch off the ground, but it still reached the ceiling.
Very wise. Here's what an Astro Blaster is. It's a stick. I'm drawing a little bit larger than real life. And at the bottom of the stick is a largish Super Ball. And then on top of that is a somewhat smaller Super Ball with a hole drilled through it so it just fits on the stick. And on top of that, a smaller Super Ball. And on top of that, an even smaller Super Ball. Mine has 5 on it. Like that. Now, you drop it, the stick is so that, to control the fact that you want all the other balls to be in a line above the bottom one, so it's not like a basketball. I had a hard time keeping them exactly vertical. You drop this thing down, and just before it hits ground, this is going at speed v. The bottom one hits the bottom. You've got to imagine that in the course of the fall, these all separated by a millimeter or something like that, which they do. This one hits the ground and reverses direction, so it's now going upward at speed v. When it collides with this one, which was going down at speed v. It picks up twice the velocity of this one, so this one goes up at 3v. That's exactly the tennis ball basketball problem. How fast is the next one? When it collides with this, it's going down at speed v. It collides with a larger ball that already has a speed in the upward direction of 3v.
7.
So it is going at 7v. Is that right? 2 3s are 6, and 1 is 7. This one here is going down at speed v. It encounters a ball on the way up, going at 7v. It is now, after the collision, going 2 7s are 14, and 1 is 15v. And the top one is going as 2 times 15 is 30, plus 1 is 31v. So that the topmost ball in the Astro Blaster is actually going 31 times faster than the velocity with which it hit the floor. So you imagine you drop a super ball down, and it comes up. Kind of impressive. You drop this thing, hits the floor, and comes back up with 31 times the velocity that it hit the floor. As I say, these things can actually be quite dangerous. And yet all it is 5 superballs. Of course, this theory is not quite right? Even with superballs, they're not perfectly elastic. Moreover, each of these balls is not infinitely heavy compared to the one above it. They're heavier. So if you wanted to analyze this completely, in fact, I had a student who once did this very elaborate, laborious thing, but they did pretend that it was truly elastic at each collision, but they put in the actual masses here, M1, M2, M3, and so on. And you come up with a velocity that's a little bit less than 31 feet, it's true, but still a very impressive velocity. This is actually an idea of practical importance too. It comes up in the case of the so-called slingshot effect. For space probes, I don't know if you've ever heard about this, but when they launch space probes that are going out to Pluto or something like that, they always use the following device. They have that space probe make a very close encounter with a bunch of planets on the way up, always figuring it so that they go around the planet when the planet is going the other direction. So let's say that this is Jupiter, and it's going at a speed w, and I have the space probe come in with a speed v. This is essentially an elastic collision. It never actually hit Jupiter, it just swung around it. I guess that's why they call it slingshot, although exactly what it's got to do with a slingshot is not quite clear to me, but anyhow, it swings around Jupiter, picks up twice the velocity of Jupiter. So on the way out, it's going now at v plus 2w. And then it heads over to Saturn and does the same thing at Saturn and picks up twice the velocity of Saturn and so on. And if you do this very cleverly, you can get the thing to pick up a jolt of energy with each encounter.
Does that mean you can start out with less than escape velocity?
I suppose it does. Yes.
Escape velocity?
Right. You know what? When I first heard about this, I thought that's nonsense. You know, it violates conservation of energy. You can't. Yeah. But the point is that Jupiter has a whole lot of kinetic energy there relative to the sun. And what this space probe did was it soaked up a little bit of that. Jupiter didn't care because it's so heavy that it still was going essentially the same velocity by the argument that I gave earlier, because the space probe is a whole lot lighter. So basically what you're doing is you're grabbing a little bit of kinetic energy from each of those planets you go around. And as far as I know, there's no reason that you couldn't.
No, I think
You got to get going in the first place, but once you get going, I think there's no limit.
I think one of the early Explorer or Voyager actually escaped the solar system using that.
Using this effect. Well, it's a clever device. That's why this thing is called the Astroblaster. It's supposed to illustrate this slingshot mechanism. Well, enough of those examples. Let me come back to the theory. The next item of theory is impulse. I want to build the theory of impulse on the theory of work in close parallel with work. So let me remind you first of all about work. Some of the stuff that I'm going to be putting here is just a reminder. Work. Force times distance. That is to say, W is equal to F delta X. Or if the force was changing, remember, and if the directions were swinging, and the work done is equal to the integral of F dot dr. But what you want to think of it as work is the integral of force with respect to time, or with respect to distance. It's force times distance. Impulse is defined in the same way, except with respect to time instead of with respect to distance. So work is how far did the thing go, multiply the force times the distance it went, or rather integrate the force with respect to the distance. Impulse is how long did it take to get there, multiply the force times the time, or rather integrate with respect to time because the force is changing. So impulse, J, is equal to force times time. That is to say, J equals F delta T, or in general, J is equal to the integral of F dt. Now I've been sloppy here. Force is a vector, time is a scalar, so impulse is also a vector. Unlike work. But it's built on integration of force with respect to a different variable. By the way, if you have taken calculus from a modern mathematician, they may tell you, oh, don't bother writing that dt there. Just write it as J equals the integral of F. Have you encountered people like that? Well, a lot of so-called modern calculus teachers will tell you, don't write that dt there. Don't write the, they're thinking of an integral of the form, integral of f of x dx. Why do you need a little dx there? Well, physicists need that d whatever it is there because I need to know, were you integrating with respect to t, in which case you're getting impulse, or were you integrating with respect to r, in which case you're going to get work. So if you're sloppy or have been taught not to write the differentials down there, get out of that habit. It's going to really make trouble for you. So J impulse is the integral of force with respect to time. Work is the integral with respect to position. Yeah. Oh, sorry.
Is it no dot product because it's a scalar?
No dot product is it? So in the case of work, I have a dot product built in here, and the result is a scalar, because dot products give you a scalar. In the case of impulse, it's an integral of a vector, and it yields a vector. So they are different in that sense. You know, I'm a little nervous about introducing the subject this way. In fact, sometimes when I've taught about impulse, I don't make any mention of work. And I'm not sure if it helps or hurts to draw the parallel, because the parallel is not quite perfect in that sense. One of them is a vector, and the other one is a dot product is a scalar. So in that sense, not quite perfect. But I'm going to emphasize the parallel for today. That's just a strategy. If it helps, great. If it doesn't, forget about it. I could have said, this is the definition of impulse, take it or leave it. Why is impulse interesting to us? Well, what is the net impulse delivered to something? I don't know if you remember because I slipped this in kind of quickly, but you remember how to write Newton's second law of motion in terms of momentum? Well, I'll rederive it. F total, the total force acting on something, is equal to its mass times its acceleration. Add up all the forces acting, that's the mass times the acceleration. But ma is m dv by dt. If the m is not changing, as typically it's not, this is nothing but d by dt of mv, right? If I differentiate that, I would have got m times the derivative of v, which is acceleration. So this is dp by dt. There's the way that Newton wrote Newton's law. Total force is equal to rate of change of momentum. Okay, let me put that into the definition of impulse here and see what I get. J, the impulse, is equal to the integral of F. Now I want to know what's the total impulse acting. That's the total force times dt, but the total force is the rate of change of momentum, so this is dp by dt times dt, which is the rate of change, which is the change in momentum. This is nothing but p final minus P initial, or if you like, delta P. Whoa, what was all that telling me? It tells me that the total impulse, the impulse due to the total force, or sum of all the individual impulses acting on something, is equal to the change in its momentum. So two things collide or so. There's an impulse delivered to the second object. That tells me what the change in its momentum is. You're supposed to think, that sounds kind of familiar. J, I'll write it here, J total equals delta P, and give it a name. That's the impulse momentum theorem. Although I'm not sure if it really deserves the title of a theorem, because it actually is a very pretty straightforward little argument there, that the total impulse delivered to something or other is the change in its momentum. But what I'm trying to remind you of course, is the work energy theorem. You remember what that said? That the work done by the total force, or if you like, the sum of all the works done by the individual forces, is equal to the change in, you tell me, kinetic energy, huh? That was the work energy theorem. That is deep. The proof of the work energy theorem is not trivial. Go back and look in your notes or in the book. The book actually has 3 different proofs building up to the general case of the work energy theorem. That's not trivial. The impulse momentum theorem, for my money, is close to trivial. But this is not. But they are in sort of a parallel here. This is work energy theorem. Gee, there's a kind of structure, parallel structure here. Let me see if I can summarize it. I probably should have done an example here. Impulse, what is it? A force, 20 newtons. Acted for 1/10 of a second. What's the impulse? Shit, I forgot what numbers I used. 20 times 10 is 2 Newton seconds. How much is that going to change the momentum of the thing that got hit? By an amount 2 G's. 2 kilograms per second. Where are we? What is the parallel structure here? Work is to kinetic energy. You use these symbols as impulse is to momentum. Work is to kinetic energy, as in the work energy theorem, as impulse is to momentum. As I said, that may be a useful way for you to keep track of these concepts, or it may not. It depends a little on your temperament, and I'm not sure that this is the best way to think about it myself, but let's try this. You know what? There was a third item, work, energy. What was the other one in that triumvirate? Do you remember? Work, power, energy. Is there an analog to power here? What was power? Power was the rate at which work is performed, dW by dt. What would the analog here be? It would be dJ by dt, the rate of delivery of impulse, or what amounts to the same thing, the rate of delivery of momentum. But what is dj by dt? It would be the guts of the integral here, the integrand, the derivative. If j is the integral of f, then f is the derivative of j. This is nothing but f. How disappointing. Nothing new here. But if we wanted to include it in the equation, power is to work, is to kinetic energy, as force is to impulse, is to momentum. So there is a kind of nice tight parallel there. Last item, I wanted to make a comment about this, or since the increase in the amount of impulse delivered is equal to the momentum, the impulse delivered is equal to the change in momentum, I can also write this as dp by dt. On one of the owls for tonight, you need to calculate what the force, for Wednesday, I'm sorry, the force exerted by a stream is. Let me just indicate how you do this, and then we'll pick this up next time. If I had a stream of pellets, or it could be a stream of water from a fire hose, I don't care. A stream of pellets, let's say, all going at velocity v, and they hit some brick wall here, let's say, and drop straight down. What average force is exerted on that wall? The way to think of it is that the force exerted on, of course, the force is going to be boom, and then nothing, and then boom, and then nothing, and then boom, nothing. It's going to be jerky, but let's say that we average over time. What's the average force delivered to that wall would be the momentum per unit time delivered to the wall. What is the momentum per unit time delivered to the wall? It's the number of particles per unit time times the momentum that each one contributes. What momentum does each one contribute? Mass times velocity. So there's a formula for the average force exerted on the wall is the number per unit time times the momentum that each one delivers.
That's only if they don't bounce back.
If they bounce back, suppose that this had been, I was assuming now that they deliver just that package of momentum, mv, and then drop straight down or stick on or something like that. Suppose that they bounced off elastically, the other extreme case, what would you say then is the force exerted on the wall? In that case, if they bounce back, the momentum each one delivered is not just mv, but 2mv, because if it bounced back elastically, so it would have been 2mv, and then I would have got twice this, because the momentum of each one delivered to the wall would be 2mv. Make sense? Think of it as momentum delivered per unit time.